The recording is back on. I will share my screen. Okay. Hoyas jueves. Sorry, I thought I could say today's date in Spanish, and then I realized I hit a wall right after today is Thursday. That's okay. I don't know 19. 19. That sounds right. Thank you. Anyways, it's week 8. We're talking strings today. This should be a pretty brief lecture compared to the other ones. So yeah, I don't know if we'll have a break in the middle of class since it's a brief lecture. Do we have any questions about last week's material or anything else pertaining to the course? Great. Then let's go ahead and get started. So the data that we're going to be using today for, I think, all of the examples is food safety inspections from the King County data repository. Note these data are fairly large. If you want to use them on your own machine, you may want to save them and load them from a local directory rather than pull them straight up from the GitHub site every time you want to run stuff. I also recommend specifying the column types so they read incorrectly. You could just use this string that I've already written here if you would like. So let's take a look at what that data frame looks like. It has 258,000 rows and 23 columns. The columns have information like the name of the business, the perhaps more colloquial name of the business, the program identifier. So I don't know Shack Coffee LLC, but I do know Shack Coffee, for instance. It has the date of the inspection, things like what kind of size of the restaurant, how many seats it has, that kind of information, where it's located, its address, its latitude and longitude, which maybe isn't that important this week, but will be very important next week. And then things like how it was inspected, what was the score of that inspection, what are some of the violations that this business had in its health inspections, that kind of thing. Cool. Okay, so we're talking about strings. A general programming term for a unit of character data is a string, which is defined as a sequence of characters. For us, particularly for social scientists, but maybe more generally for our users, the term string and character data are mostly interchangeable. There are very few cases where string and character data are distinct terms. In other coding languages, string often also refers to a sequence of numeric information, such as a binary string. We rarely use these in R, so I'm not going to be talking about strings referring to a sequence of numeric information. Note that these are sequences of numbers rather than single numbers, and thus are strings. You can think of them as being like, you know, a phone number or a zip code, that kind of thing. One thing that separates a string from a number is that the leading zeros are meaningful. So a zip code that starts with 0, I don't know where that is. New York, maybe? DC? I don't know where the zip codes start. Leading zeros are meaningful in a string rather than as a number. Okay. Now that the sort of nerdy caveats out of the way, let's talk about some string basics. So we've used this n character function before. We use it to get the number of characters that are in a string. For instance, we can say how many characters are in the zip codes in our restaurants data. So we'll take the restaurants data and then create a new column called zip length that's equal to the number of characters in the zip code column. And then we'll count. This is a shorthand for grouping by and tallying all of the distinct combinations of the amount of characters in the zip code column. And we see that we have returned a table with 2 rows and 2 columns, where the zip code length was 5. There are 258,629 rows. And when the zip length was 10, there is 1 row. So that's just one of those weird like 98115-4326 situations. We've also used the substring function. This is a base R function. We've used it a couple of times in the homeworks and examples. We can use it to pull out just the first 5 digits of the zip code for everyone to make sure that we don't have that one that's just has the dash and then some extra information that I typically don't need when I'm like using MapQuest. So we're going to assign to the restaurants object the restaurants data and then mutate a new column called zip5. We'll take the substring of the zip code column for everything between the 1st and the 5th character in that column. And then when we look at the first 5 distinct zip codes, we'll get 98126 and 98102 and a lot of other sort of King County and King County adjacent zip codes. We can combine parts of strings together using the paste function, for instance, to make a whole mailing address. So I might have used paste before. I can't think of a current example. I tend to use paste 0, which we'll talk about. So here I'll assign to the restaurants data, and then make a new column called mailing address. That's equal to the paste together of the address column, a comma with a space, the city column, a comma with the state space, the zip5 column, and our separator is going to be equal to quotes with nothing in them. And then when we look at the distinct mailing addresses, and the first 6 of those, we have mailing addresses that include the city and state and zip code. Things like 2920 Southwest Avalon Way, Seattle, Washington 98126, or 1225 First Ave, Seattle, Washington 98101. And this tends to be tremendously useful. I don't tend to use the paste function, like I said, so I think paste 0 is here. Yes, so paste 0 is a shortcut for paste without any separator in it. I tend to not like to deal with the kinds of spacing that paste asks you to deal with, and it adds a space in between things. Like after wa here, the space would not go if there was not the sep here. It's too much for me. I tend to just use paste 0. So here, if we look at how paste works with pasting together the first 5 numbers and the first 5 lowercase letters of the English alphabet, paste adds 1 to A and makes a string 1 space A, and then 2 to B with a space in between. And if we wanted it to have no space in between, we would say paste 1 to 5, the letters A through E, and then sep equals quotes with nothing in it, and we would get 1A with no space, 2B with no space, and so on. Whereas paste 0 allows us to not have that separator. And then if I'd like to add spaces, I tend to do that post hoc. Is that all making sense so far? Sort of regular base R functions for dealing with strings. Okay. So the separate argument within paste controls what happens when doing entry-wise squeezing of vectors you give to paste, while the collapse argument controls if or how they go from a vector to a single string. So here are some examples. Make sure you understand how each set of these arguments produces its results. So in the first example, we paste the first 5 letters of the English alphabet, lowercase, and collapse on the exclamation point. And this will create one string with all of our elements separated by their exclamation points. Okay, so this is just one string. Then paste the first 5 numbers and the first 5 lowercase letters and separate them by a plus. We'll create 5 elements of a character vector where each of these are pasted together with a plus in between. Paste 0 with these first 5 numbers and these first 5 letters collapsed on 3 question marks will create one string. And then this will show the recycling of paste. And we'll create 5 elements for each of the things that's getting recycled. Whereas this one will paste and create just one string since it's using the collapse argument. Okay, let's get into talking about stringer. I don't tend to use a ton of any other sort of text processing than stringers. Yeah, shout outs to The Wire. Stringer is yet another R package from the tidyverse, like ggplot2 and dplyr and tidyr and lubridate and reader. It provides functions that replace some basic string functions like paste and end character in a way that's a bit less touchy with missing values or factors. It's really easy to remove white space in between things. So if like you have a character string and you're not sure if there's 2 spaces or 1 space in between 2 things and you'd like to get rid of that extra space, it's really easy to do that. Or if you'd like to add spaces places, it's very easy to do that. You can perform tasks related to pattern matching, that is detecting patterns in your character data, locating where patterns happen, extracting particular matches, matching specific columns together, replacing character strings, splitting columns by characters, that kind of thing. These functions use regular expressions to describe patterns. So a lot of things that would be very easy for us to describe using our words, computers are very touchy about understanding that. So we're going to be using regular expressions to help express ourselves to the computer so it understands what we mean when we're talking about character strings. I also tend to find that the base R and stringy versions of these are harder to use. Conveniently, most stringer functions begin with this prefix str_, and this makes R Studio's autocomplete way more useful. I tend to forget what all of these stringer functions are called, so I just do str_ and then I scroll through until I'm like, oh, I think I'm looking for replace all. So let's talk about a few equivalencies before we get into some specifics. So string_sub is like substring, but also lets you put in negative values to count backwards from the end. So I think I showed an example of this in the lab earlier. Yeah. So for instance, we could say string sub the word Washington from the first to the -3rd entry. It will start at the end here for this end argument and count backwards. So it gets rid of the last 3 parts of that character string, or ends on the 3rd one. String_c is string combine, It's just like paste, but where the default is sep equals quotes with nothing in it. So it's like paste 0 in that way. String length is equivalent to n character. So here, n character weasels, 7. String length weasels, 7. It's also quite easy to change cases using these stringer functions. There's the string to upper, string to lower, and string to title to convert cases, which is often a good idea to do before searching values. For instance, in our restaurants data, if you look at the unique values in the city column, you can see things like Seattle with a capital S and Seattle all caps. It can be very difficult to say filter equals Seattle when this is your situation, right? So one thing you might want to do is say, overwrite your restaurants data and then mutate across some particular columns, the name, address, and city, and just make them all uppercase, all of them. And that way it'll be way easier to search for things or to filter by things. I will say that I tend to make everything lowercase. That's just a preference. You could also be somebody who turns everything string to title, and then it will always look like this. I hazard against this because of like Washington, D.C. can get annoying for stuff like that. There's also string to sentence. This converts cases for a first character capital letter, which may be a good idea for modular reports, but beware the way it coerces things. So here I'm going to make an elegy vector. I'm going to take the restaurant's data and then filter to 1401 Northeast 42nd Street, which you might know is right over that way, and take the first row of that and then pull the name of the business and then string to title and say, I miss you. This is the data that I'm pulling here, and a period at the end. I miss you, Madeline Bakery. And then you can string to sentence, I miss you, Madeline Bakery. But note that it has also changed the capitalization of Madeline Bakery here. So string to sentence will not recognize things that need to be capitalized. But I do miss Madeline Bakery. Do y'all recall Madeline Bakery? Were you here for that? You missed out? What was good about it? It had everything. So like, it was a good place for lunch. It was a good place for coffee. It was a good place for tea. It was a good place for little baked goods. It was just excellent. And it was just right there on the app. You didn't even have to go all the way to the app to get there. I particularly liked getting the Poke Bowl there. I think that the Poke Bowl in Seattle is too bougie, is probably the word I would use. And they didn't behave that way. I'm tired of Poke Bowl places that have too many fixins. Back in the motherland, Poke Bowl is normally just rice and fish and one ingredient or two, maybe spicy or not. And Madeline's Bakery knew that. Anyways, the string trim function deals with white space. Extra leading or trailing white space is common in text data. So you might see, look at the unique restaurant names here. Things like At the Shack LLC has a trailing white space, but it's often very difficult to tell with our eyes that stuff like that is going on, especially when we have, 258,630 rows or what have you. So any character column is potentially affected by this kind of situation, especially in administrative data. We can use string trim to clean them all up at once. So we could say, override our restaurants data and mutate across where is.character, so every column in our data set that is a character column, string trim will remove leading and trailing white space. And now when we look at the unique restaurant names, and the first four of those, At the Shack LLC does not have the trailing white space at the end. There's another function that I can't recall if I made a whole slide for it, but it's called string squish, and it gets rid of white space that's in the middle of strings. So anytime there's like duplicate spaces between things. Okay, now we're going to get into talking about regular expressions and pattern matching. Do we have experience with regular expressions already? A little bit, okay, cool. So what are regular expressions? Regular expressions, or regexes, are how we describe patterns we're looking for in text in a way that the computer can understand. We write an expression, apply it to a string input, and then compute with matches we find. So there are two kinds of characters that we need to look out for when we're writing regexes. One is literal characters. These are defined snippets to search for, like when we look for SEA in our homework 5 or 206 area code or something like this. And then there are meta characters, and they allow us to be flexible in describing patterns. So the backslash, the caret, the $, the period, the pipe, the question mark, the asterisk, the plus sign, the parentheses, square brackets, and curly braces all have particular functions that they do, that they fulfill while making regular expressions. So since they're separated in order to make regular expressions work, if you wanted to match by them as a literal character, you must escape it with two preceding backslashes. So if we wanted to match 206, but in parentheses, but parentheses here are like a special meta character that we need for particular purposes in our regexes, you would want to include two backslashes before those parentheses in order to match this string. I know I'm saying kind of a lot. We're going to go through more in-depth examples than this, but just suffice to say that we will need to escape special characters if we want to match them. One reason we might want to do this is to detect some particular set of strings. The string detect function is great for doing so. It will return back to us a true or false when a match is found. So let's say I want to get inspections for coffee shops out of our data. I'll say a coffee shop is anything that has coffee, espresso, or roaster in the name. And the regular expression for this is going to be coffee, all caps, because recall we made our data all caps earlier. Coffee, or espresso, or roaster. And recall that this or is like when we were learning how to use filter before. Because the pipe, it's called pipe when we're talking regex, is a meta character, that means or, use the string detect function, which returns true if it finds what you're looking for and false if it doesn't. It's very similar to grepl in that way, if you're familiar with grepl. But now we can say, assign to this coffee object, the restaurant's data, and then filter, and we can just put in here a string detect, the column for which we would like to detect some information, and then this regular expression of coffee or espresso or roaster. And the spaces matter when it comes to this pipe setup. And what we'll get now out of our coffee object, we can get the distinct names and look at the first 6. We have 2 Sisters Espresso and 701 Coffee and 909 Coffee and Wine and AJ's Espresso and Alki Humfront Smoothies and Espresso and All City Coffee. Pretty neat. Let's say you have some pressing issues about your coffee. Let's take each unique business identifier, keep the most recent inspection score, and look at the histogram of scores. So now we can take the coffee data and then select the business ID, the name, the inspection score, and the date. And then we'll group by the business ID and filter to date equals max date. This is giving us our most recent date. And then we're going to deduplicate by saying distinct dot keep underscore all equals true. And then make a ggplot with the inspection scores on our X and 8 bins for our histogram. And we can see that by and large, there's nothing going on at coffee shops. They're a pretty safe place to be as far as inspection scores go. Yeah, that's not going to be the reason your coffee might injure you. It's the pot a day that is probably more dangerous. We can also use string detect on patterns. So let's look for phone numbers whose first 3 digits are 206 using string detect. We'll want it to work whether they have parentheses around the beginning or not, but to not match when there's a 206 somewhere else in the phone number. So one way we can do this is by making a pattern. This is a pattern, or this is an object where I will assign my pattern. This is a regular expression here. We'll get into what's going on in a second. And then we'll say phone test examples is going to be this number, which is just a string of numbers. This phone number, which is 206 in parentheses. This one that is 206, then a space, then the first 3 numbers of the middle part of the phone number, and then a dash, and then 206 in the middle of a phone number. Now we can say string detect our phone test examples, so this vector of phone numbers here, and then our pattern is going to be the pattern regular expression I created above, and it will return true for this one, which does have a 206 in the front, the second element, which also has 206, but in parentheses, and the third element, which has 206, then a space. But it does not return true for 206 being in the middle of the phone number. So this is really neat. Again, I think that this is something that really makes me feel like computers aren't that smart. A lot of our things make me feel like, oh, wow, computers know everything. And now I'm just like, come on, man, I just want like 206. But the pattern. So the way that this was written, at the beginning, there's this caret. The caret is a meta character, meaning look at the beginning of the string in order to match the next stuff. Okay, so it was not going to check things that were not the start of the string. The // open parentheses question mark means look for a left parentheses. So look for just this or just this. But since there's a question mark afterwards, it's optional. And then the number 206 is the literal string to look for after the optional parentheses. So this is going to return true when 206 is in the beginning, and if there's a parentheses there or not. And if it's 206 anywhere else, it's not even going to check. It's just going to say it's wrong. So as soon as it saw 5 here, it said this is false. Question?
If you didn't do string trim beforehand, would this still work? Like if you had a space and then a 206?
I don't think it would. But actually, let's just try. Okay, so this is that example, true, true, false. And now we will add a space in front of this first one. Yeah, it doesn't know. Okay. The string view function is really excellent while you're trying to learn how to write regular expressions in particular. It allows you to see in the viewer pane exactly what text is being selected with a regular expression. So what will happen is when you run something like this, it will generate a small web page in the viewer pane. This will not work within your Markdown document, so you will have to figure out another way to get it to take a picture of the viewer pane and put it in your Markdown. This is really great because it will check for stuff like, okay, 206, 206, 206. Doesn't even register here that the 50555 could be a thing. Just be careful not to load an entire or like a really long vector or variable. It might crash your RStudio as it tries to render this really massive picture of all of these highlighted pattern matches. That's neat. So perhaps we want to know how many phone numbers aren't in the 206 area code. We could use string detect to find that information out. We could take the restaurant's data and then make a new column called has a 206 number. It's equal to string detect the phone number and then the pattern that we wrote earlier, and then count each of those. And so we see that far and away, there's more true 206 numbers in our restaurant's data set. But the thing to note here is that string detect returns NAs for rows with missing phone numbers because you can't search for text in a missing value. So it's not going to say like, even if you wrote a regex that said NA, I don't think it would look for it. The string extract function extracts substrings that match a particular regular expression. So let's extract the directional part of the Seattle addresses, which reminds me, this is always wild to me. Okay. How is this correct? This is how like the streets are numbered, but like this is West Seattle. I feel like it shouldn't be Southwest. This isn't West Seattle. This is just Queen Anne and stuff, you know? I don't know. I was just thinking about it when I was making these slides and I was like, this is wrong. Something wrong here. Anyways, where are my slides? Here they are. Okay, so we want to get just the directional part of the addresses so that we can identify where they fit into those colored blocks, even though I disagree with how they're allocated. So we can make a regular expression that we're going to call direction pattern. That's going to look like this, which is the directions as ors going clockwise inside of parentheses, and then some other stuff. Don't worry about it so much right now. I'll explain it in a second. And then we're going to have direction examples, which are going to be these four streets. 2812 Thorndike Ave West, 512 Northwest 65th Street, 407 Cedar Street, and 15 Nickerson Street. And now, if we run string extract on this vector of addresses, and then use the direction pattern to know what to extract, it will extract the west from Thorndike Avenue West and the northwest from 512 Northwest 65th Street, and return NAs for the others. So the first space will match a space character. So we expect, knowing what we know about addresses, that there's going to be a space before a west or a northeast or what have you. Then this whole section within parentheses matches one of the directions in the group. So it's going to pick one of these things, one that it's found, it's going to search for each one. And then there's this other set of parentheses here that is a group saying either there is a space after the match of these things in the first group, or it's the end of the string. So that's what this $sign is doing. So it's either the case that you have something like Thorndike Avenue West, where there's a space above before, it matches one of the things in the first group, West, and then is there a space after, or is that the end of the string? And since it's the end of the string, we're going to match the W. But here for 512 Northwest 65th Street, there's a space before, it matches the Northwest, and then it detects that there's a space after, and it's going to take that and keep both of those. Okay? Is that making sense? That the $sign will detect the end of the string for you, just like the caret was able to detect the beginning of the string. Cool. Okay, so let's answer the question then. Where are the addresses? So we can take the restaurant's data and then get all of the distinct addresses and then mutate a new column called city region. And it's going to equal string trim, the string extract of the addresses and the direction pattern. The reason I'm putting string trim around our string extract is to avoid this problem, which is that there's a string or there's a space here and there's a space after or before here and after here. We want to get rid of those in order to group all of our addresses together. And then we're going to count our city regions in a range in descending order of n. I'm realizing I could have just made this slightly less code. That doesn't matter. But we can see that most of the restaurants in this data set are in the northeast part of Seattle. So like where I'm sitting right now. And then second most is in the south part. The next highest is none of these. So we imagine that there's a lot of restaurants that are in like Midtown. Like that's where Guy Fieri's Flavortown Kitchen is. And other excellent Seattle places to eat like that. A common operation is to string extract something with extra spaces and then trim them out, all of the extra white spaces. Because it tends to be pretty easy to find something that's between white spaces, but you don't actually want those white spaces, but the white spaces matter for finding the thing in between them. Yes.
If you did a string extract, that pipe to string trim, it's the same.
Yes. Okay. The string replace function allows us to do exactly what it sounds like. Just replace some matching string with another argument that we supply. So maybe we want to do a street level analysis of inspections, something like compare the Ave with Pike Street. How can we remove the building numbers? So one way we could do this is by using this regular expression here, which is yet more jumbly and complex than the last one. And then we are going to use this number pattern on these examples, which are going to be 2812 Thorndike Avenue West, First Ave, 10A First Ave, 10-A First Ave, 5201-B University Way Northeast, and 7040 1/2 15th Avenue Northwest. So we're going to string replace our numbers example vector with our numbers pattern to know what we're going to replace. And then our replacement is going to equal quotes with nothing in them to get rid of those building numbers. Okay. So now what we'll get from this vector is Thorndike Avenue West, First Ave, First Ave, First Ave, University Way Northeast, and 15th Avenue Northwest. So this regular expression is kind of a lot. Let's break it down. One thing I also want to note is that I'm hoping to expose you to regular expressions and sort of all the power that they have. I don't feel like I'm a great wielder of this power. I think that there are a lot of really interesting and cool ways to write regular expressions to do cool stuff. I typically just get it to do stuff as cool as this and nothing cooler. So if you have a really complicated regular expression question, I have people that can help you better than me. But if it's something like an address, I can totally help you. Also note, so I've said replace with quotes with nothing in them in order to get rid of these things. You can just use the string remove function to do that same thing. We'll skip a step. Okay, so how does this building number regular expression work? So first, we look at the start of the string, and then in brackets, look for 0 through 9, meaning look for a digit between 0 and 9 at the beginning of the string. Okay. Next, we have this asterisk, which means potentially match more digits after that as many times as there are digits. Okay, so this is going to keep looking for the thing right next to it that was looking for something until it runs out of matches for that. So if we had a building number that was like 18 digits long, it would have been able to detect that and remove that if it wanted. Next, we have the dash question mark, which means optionally, question mark means optionally, match a hyphen for the cases that we have a 5201-B situation. Next, we have in brackets A to Z question mark, which means optionally match a letter A to Z. We don't anticipate that there's going to be more than just those one letter, so there's not going to be an asterisk at the end of this. Then we match a space, so the space matters here, right? And then in parentheses, so as a group, check if there is a 1/2 and then a space. So this will optionally match a 1/2 for like a, I forget the term. I don't watch a lot of renovation shows, but for when there's like a house that's smaller and like in someone's backyard.
A dadu.
A dadu?
It's like dwelling adjacent unit or something.
I'd never heard dadu before.
Okay,
I was thinking it's something like it's like a mother-in-law unit. Yeah,
Oh,
yeah. That's the one I was thinking. I'd never heard dadu. Okay. That's pretty tight. Okay. Okay, so optionally matches a 1/2 followed by a space. Since this is apparently a thing with some address numbers. I don't know. I'm from in the sticks, and there's just like you just have two properties that get the same mail. Who cares? Anyways. So we can remove street numbers in our restaurants data by overwriting our restaurants data and then mutating a new column called street only. That is the string remove of the address column using our number pattern. And so now we can look at these first 10 distinct addresses, and these are just going to be things like Avalon Way, Mercer Street, and then there are some curious cases of like Fairview Avenue North Unit 1700A. So how are we going to get rid of those? Getting rid of unit and suite references is tricky, but a decent attempt. Again, I don't feel like I'm the greatest wielder of regex, but I think this is a decent attempt. Would be to drop anything including and after a number, STE, suite, shop, or unit. So I'll create a regular expression that starts with a space, and then in the first group, anything that's pound sign, STE, suite, shop, or unit, then dot, asterisk, $. Okay, we'll break it down in a second. And then our examples are going to be First Ave, Rainier Ave South, Unit A, or number A, Fauntleroy Way, Southwest, Suite 108, number 100C, and 54th Street. And we were able to successfully get rid of those using this regular expression for First Ave, the Rainier Ave, Fauntleroy, 4th Ave, and 54th Street. So how did this work? First, we matched the space. Then we said, as a group, match one of these words, one of these literal strings. Then dot, asterisk, $sign matches any character. So dot will match any character after those words. So after pound, STE, sweet, etc. 0 or more times. So it'll keep matching anything that occurs after the word unit, for instance, as many times as it occurs until the end of the string. So that's what the $sign is doing. So this is just a way to search for anything that matches after the things in the first group until the end of the string. And we can use that to remove units and suites. So we'll overwrite the restaurants data and then make the street only column. String trim, our removal of the street only column that we made in the couple slides previous, also using the unit pattern. And we'll see that we still got C-08 here that was not captured by the regular expression that I wrote earlier. And that's something I want to highlight when it comes to writing regular expressions, is that it's often a lot of just trying to make sure you can check back all of your little issues. It's a very iterative process, and you're not going to get them all the first time when you have goofy admin data a lot. Question?
With a data set of like 2,000,
Mhm.
how would you, what's your approach for checking like across the whole data set?
Sure. So since I would say that breaking it down into situations like this, where it's just like, I'm going to make sure my regular expression looks at the beginning for this particular thing, and then I would just keep looking at like the first 11 and the bottom 11 or the middle 11 and seeing how that goes, and then breaking it down to like, okay, I need to get rid of the things at the end that have this like goofy situation. And then sometimes it will just be sort of patchwork by the end. Okay, so an important question here we might have with this data set is, where does danger lurk? So let's get the number of 45 plus point inspections occurring on every street. So we'll take the restaurants data and then filter for the inspection score being greater than 45, which is quite high for our data set. And then get the distinct combinations of the business ID, date, inspection score, and the streets that we've now regular expressioned all the way down to be able to look at particular streets. And then we're going to count by grouping the streets and how many rows are on those particular streets. And we can see that it looks like the Ave is like pretty up there in this data set, which is fine. I'm not going to stop eating there. South Jackson Street. I'm trying to think of where I eat it on South Jackson Street. There's that Philly cheesesteaks place. That's really good. Is the crawfish place on South Jackson? I think it is. Okay. Anyways, so let's talk about splitting up strings. You can split up strings using the tidier separate function seen in week 5. Another option is to use the string split function in the stringer package, which will split strings based on a pattern separating parts and put these components in a list. So separate's really great for when you want to make two new columns. But if you want to take the components and put them in a list, you want to use string split. String split fixed will do that both a matrix instead, and thus you can't have varying numbers of separators. So let's look at an example here. We can split fix the violation description based on space hyphen space, and n equals 2 means how many sets of splits are going to be made. And so here it will be things like violation 4300, non-food contact surfaces maintained and cleaned, or violation 4100, warehouse or washing facilities properly installed. I find this to be pretty useful to do when you have like there was a paper I was working on that was looking at a bunch of union ballot information, and I wanted to separate them so that I could tell very quickly whether or not the union ballots were in English and Spanish, or in just Spanish. And I was using string split fix to break them apart based on the case numbers on each of the ballots. But I don't think that I run into a problem that needs string split all that often. I tend to use separate. One thing that you may want to do is make sentences. Maybe we have a report or website where we need text dynamically generated from the data. So let's prep some of the recent scores in order to show how we might do that. So we'll make this recent scores data frame by selecting the name, address, city, inspection score, and inspection date from our restaurant's data. And then we're going to get rid of all the inspection scores that are in NA. We're going to group by the name of the business, and then arrange in descending order of inspection score, and keep just the first one. So we're just going to keep, I think this is taking the most recent score per business. We're going to ungroup that, and then we're going to mutate for all of our name, address, and city to make those text strings into title text, and then convert our dates into date POSIX time format. And we're going to look at a sample of a few of those. So one way we might think to write these sentences would be using the paste function. We could do something like take our recent scores data and then make a new column called text description, and then paste our name in quotes is located at the address in city and received a score of the inspection score on the month function on our inspection date, and then paste 0 the ordinal day of the inspection date and the year. And so we'd get something like Supreme Bean again is located at yada yada yada, et cetera, et cetera, et cetera. One thing I would say that you might want to use instead would be glue. We can use string glue as paste's more sophisticated sibling, which uses the glue package. Variables and functions just go inside of curly brackets, and you can create temporary variables for convenience. Okay, so one thing you can do is say string glue, and then in curly brackets say name, and in curly brackets say address, and this will say look back into my data set and look for those particular columns, right? So this isn't that different from the paste version. But then you could say, make this when variable for when you're writing the sentence, and then down here specify what when means. So here I'm just showing you that when meaning the inspection date, but you can make it do far more complicated operations for these temporary variables that you use within the sentences. Another thing that I like to note is that you can make the things in quotes as long or as short as you want, and then put a comma after, and it will still make them the same sentence length. So you can make the blocks of text quite small, and it will still make the sentences the correct length. I think this makes writing the code a lot easier, because you can separate when things are going to be in curly brackets by commas, or separate the things like ordinal, day, when, etc., etc. To be more pleasing for a peer or a collaborator, that kind of thing. I would also highlight the string wrap function here and the \n. So the previous output will work fine for, let's say, an inline markdown, but it runs off the edge of the console. Like, if you can't tell, like, I couldn't even finish reading the sentence here. It also won't wrap in many tables and images. So if I wanted to use this to be the caption of my ggplot, for instance, it might run off the edge of the ggplot, and we wouldn't be able to figure out how to keep it on the graphical space. The string wrap function can add regular line breaks, or you can manually add them in using the \n. So here, we'll take the score text and then pull our text description column so that it's a vector, and then use string wrap width 70. So we're specifying the number of characters that we would like to wrap the sentence around. And then we can say, like, paste 0 2 line breaks as a paragraph break in between our contents of our pulled text description vector. And then cat will combine the text all into one string and then print it. So now we have Supreme Bean again is located at 14424 Ambaum Boulevard Southwest in Burien, and received a score of 10 on January 24, 2017. Mandarin Garden is located at 40 East Sunset Way in Issaquah, and received a score of 72. Oh, goodness, in 2007. And Flapjack's Waffle House is located at 13806 First Ave South in Burien, and received a score of 45 on October 3rd, 2008. And it's all in one little paragraph. That's one string. A few other useful stringer functions that I'd like you to know about are string pad. It takes a string argument, width, what side you're going to pad, and the pad. It adds padding, that is space, to any string to make it a given minimum width. So if you have a very particular width that you need your strings to be, but some of them only have 2 characters and some of them have 15, but they all need to be the width of 18 characters, string pad can get you there. String subset returns all elements that contain matches of the pattern. So this is really great when you are like just trying to make a column that tells you that inside of this other column there is some string match, but I don't need to take it out or get rid of it or anything. String which returns numeric indices of elements that match the pattern. So maybe you need to know within your string that the pattern is in the 3rd element in this cell and the 4th element in the, or the 4th character in the next cell, that kind of thing. That's what string which will provide you. String replace all performs multiple replacements simultaneously. So if you have, let's say, a bunch of leading zeros, but you want to get rid of those, you could say string replace all 0 replacement, I don't know, quotes with nothing in it. It'll get rid of all of the zeros instead of just the first match. And then string squish. So I'd mentioned this before, trims the space around a string, but also removes the duplicate spaces inside of it. And coming up, we have homework 6, part 2, that's due next week. Peer reviews are due the week after. That's the last mandatory homework. Homework 7 is optional, and that's the last of the assignments. Do we have any questions? Cool. I think that maybe next week, yeah, it's week 8. I think maybe next week you might be getting the evaluations things. Please fill those out. I'd really appreciate it. But that's all for me. Thank you all so much.